go over 9.1 beta, which is how to take a geometric series and differentiate the series term by term and anti-differentiate the series term by term. So we'll go to the PowerPoint. And you're given this, ready? So it's a geometric series where we have the first term is 1 and the constant multiplier is x. We have first term divided by 1, subtract the constant multiplier. So we have 1 times the constant multiplier is x. X times the constant multiplier, you get x squared. Okay, and we want to find this, which is 1 divided by 1, take away x, quantity squared. Well, what is that? If I differentiate the left side, ready, you would have the derivative of mu to the negative 1, which is negative 1 mu to the negative second times d mu. The negative ones would multiply to 1. That's what we're trying to find. So what we're trying to find is the derivative of the left side. So we just differentiate the right side. So we take the derivative of the right side term by term. The first term, 1, differentiates to 0. This x differentiates to 1. X squared differentiates to 2x, and so on. Okay, and this series would represent this function, which was the derivative of what was given. Then in example 5, it takes something a little different. First term's 1. 1 subtract the constant multiplier. In this case, the constant multiplier is a negative x. So our series would be 1 times a negative x times a negative x squared times a negative x. And we want to find the natural log of the denominator. So I'm going to anti-differentiate the left, which would give me what I'm looking for. So we substitute x, we substitute a t as the dummy variable as a placeholder. So all we did was we rewrote this top line, and we substituted the x with a t, so we can tell where our work is involved with t's, and then when we substitute the x, we're back to what we're trying to find. So we anti-differentiate this from a constant to x, both sides. And we do this, ready? On the left side, we would get ln, the denominator, from the upper limit, subtract the lower limit. On the right side, this 1 is dt, so this 1 goes to t. This is negative t to the first. 1 plus 1 is 2, divided by 2, negative 1/2 t squared, and so on, from 0 to x. So the left side, we put in the upper limit, subtract the lower limit. And the lower limit is going to be ln 1, which is 0. And the right side, we put an x in wherever there's a t, subtract, put a 0 in. Where every time we put a 0 in, there's a variable there, so that's going to subtract the 0, so that's not going to affect it. And we're going to be left with what we're looking for, the natural log of mu. And the series for that would look like this. And there's our interval. Okay? So if we go to the PDF, this is the work step by step that you just saw in the PowerPoint, where the common ratio is negative x. And it's taking us here, and the general term, because the signs are alternating, is negative 1 caret n, x to the n plus 1 over n plus 1. Okay? So this is what you want to familiarize yourself with when you go to problems 21 and 31 that are paired up. And we're going to ask you in 31 to anti-differentiate the expression in 21. So you can pause the video and then use this as the model, example 5, in order to anti-differentiate what you got in 21. So for 21, here's the question. And you notice that you have two different bases raised to the same exponent. And you know that you can distribute an exponent over multiplication. So you can rewrite this as 2 caret or 2x caret n. So that's your constant multiplier. So that has to be between -1 and 1. We divide a 2 through, and that gives us our interval, -1/2 to 1/2. So here's our function in y1. Here's our fourth order series in y2. And we see we made looked at the window, or we looked at the table here. And at -6/10, which is outside the interval, the values are very different. But as you get inside the interval, how close you are to y1 and y2. Okay. And then what we want to do is take this expression and anti-differentiate it. So if you need to pause the video again and go back to example 5, do that. And when we move on to 31, we want to anti-differentiate this term by term. So we have 1 divided by 1 subtract the constant multiplier, and we're using the t as a placeholder. So then this 2t is the constant multiplier. So the first term, we have 2t caret 0. This is telling us start at 0, or the lower limit 0, the upper limit's the variable. 2t caret 0, 2t to the first, 2t to the second. All right. So this would just give us exponentiate to a 1, 2t, 4t squared. When we anti-differentiate that, this is 1t to the 0. Replace the exponent with 0 plus 1, divide by 1, and you would get, this goes to an x to the first, divided by 1, 2t to the first, 1 plus 1 is 2, divided by 2, and you would get, replace the t with an x after you anti-differentiated, you would get 2x squared divided by 2, so you would get this expression, where the general term would be 2 caret n, starting at the 0 term, x to the n plus 1 over n plus 1. When we anti-differentiate the left side, right, our denominator is mu. The derivative of mu with respect to t is -2, so d mu is -2 dt. I have dt, so I need a -2. This is anti-differentiation by substitution. So to balance that, multiplying this dt by a -2, I got to multiply by -1/2 out front to give the identity element multiplication. So the expression goes to -1/2, 1 over mu d mu, which gives me -1/2 ln mu plus the constant. So this function can be written as this series, and we put them in, right? y3, the fourth order series, and y4 in the interval from -1 to 1. Okay? So, thanks for watching.